So jumping forward a little bit, J.J. Thomson, late 1800s, made something called a cathode ray tube. And here we have a photograph and a diagram. What this is a partially evacuated glass tube, and you apply a high voltage across the ends. In a way, it's kind of like a fluorescent light, but a little bit different. And so what he found was that you apply this high voltage and a beam of light goes from one end to the other. This is the cathode, the negative terminal, and this is the anode, the positive terminal. And because the rays were coming from the cathode, they were called cathode rays. They were rays coming out of the cathode. And then, this happens, and then, okay, what can we learn about this weird phenomenon? He found that the particles in that cathode ray had several properties. They traveled in straight lines. They were independent of the composition of the material from which they originated. So you could make that cathode out of lead or iron or stainless steel. It didn't matter what you made it out of. The cathode rays were always the same. And the cathode rays carried a negative electrical charge. So electrical charge is a fundamental property of some particles. And it results in attraction and repulsion between particles. I had an interesting discussion with a friend at church, and it came down to talking about electrical charge, and he's like, but where does the energy from that come from? It's like, there's no energy involved in that. It's just a fundamental property of these particles. And he just, could not get his mind around that. And I don't blame him at all, because it's a very weird idea. So, electrical charge. Particles can have a positive or a negative charge. A lot of things are neutral. But we have particles that have positive charges and negative charges. Opposites attract. So opposite charged particles are attracted to each other. If we have two positive particles, they're repelled. Two negative particles, they're repelled. So electrical charge is not the same as magnetism, but it behaves in many of the same ways, and magnets are something we're a little more familiar with, right? So remember those little magnetic trains? The Brio trains, and they hook together with magnets. If you turn the car the other way, it won't stick to the locomotive, because you've got a North Pole and a North Pole magnet together, and you can push them together, but then they'll fly apart. Put a South Pole and a North Pole, and they click together. That is a fundamental property of magnets. That's what they do. Electrical charges behave in a similar way that opposites attract and like charges repel. So because these particles had negative electrical charges, that caused them to behave in a certain way. Yeah?
Talking about products, could it also be said that because they have electrical charge, it's actually creating the properties of magnet?
Electrical fields and magnetic fields are related. You can use a magnetic field to create electricity. You can use electricity to generate a magnetic field. But that's not going on here. These are just the fundamental properties.
What was that guy at church trying to say?
Well, he was wondering what holds matter together. A piece of iron. Why don't the particles just fly apart? Where does the energy come from to hold the particles together? And I'm telling him that there's no energy required to hold the particles together. They are attracted to each other, and they're actually at a lower energy state when they're combined. But, it had been a long time since he had any science in high school, and so it was an interesting discussion, yeah. I was impressed with his curiosity, yeah. So Thomson studied these cathode rays. He was able to look at the charge to mass ratio of the ray particles by deflecting them using electric and magnetic fields. So you can get magnets to move in electric fields, and you can also get electrical charges to move. So here he generates the cathode rays. Winter, come on. Here it is. And here's a magnet and then electrically charged plates. And by manipulating the magnetic and electrical fields, he can cause this beam to move and get deflected. And this really is the principle in the old CRT televisions, the ones that were really deep. Remember those? You know what CRT stands for? Cathode ray tube. It's a cathode ray tube. And so the way those things worked is they took cathode rays and using electrical and magnetic fields caused that beam to go back and forth across the screen. And as it hit the screen, it would change the color of the screen. And that's why those old televisions had very low resolution. If you talk about the number of pixels, tall and wide, it was really quite small. And you could actually see the little squares, right? But that's how CRT televisions work. So he was able to figure out that there was a charge of negative 1.76 times 10 to the 8th coulombs per gram of those particles. So, you know, that's cool, but of limited usefulness. A coulomb is a unit of charge. That's all we need to know about it. What was crazy about this, though, was that this implied that that cathode ray particle was 2,000 times lighter than hydrogen, the smallest known atom. So he's messing around with some particles that are smaller than atoms. And the atom was supposed to be the smallest building block of matter. So this was like mind-boggling, right? The indestructible atom could be chipped. So in this experiment, he's basically chipping off pieces of atoms and shooting them through space. Very, very crazy. What he had discovered were electrons. Electrons have negative charges. They have very low masses. These electrons are particles that are present within all atoms. So up to this point, the atom was like we think of a Lego brick, just a solid piece of something, right? And now this is the first evidence that that atom is actually composed of smaller particles. That was a very, very big idea. In 1909, American physicist Robert Millikan did an experiment with oil drops. And using Thomson's charge to mass ratio, he was able to find the charge on a single electron. So I've got a video and this picture. I'm going to tell you about the picture first, and then we'll watch the video, and hopefully between the combination of those, you'll get a general idea of how and why this worked. I'm not going to test you on the details of this experiment, but I think these early experiments are simple enough that we can at least get an idea of how cool it was. Because one of the things about science is that we're trying to discover things, learn about things that we can't see, right? And so how do you find out about something you can't see? Well, it's a big puzzle. So what happened here is he had an atomizer. So this is like a perfume atomizer, but there's oil in here. And so you squeeze this, and this cloud of oil particles shoots out. Very, very fine mist of oil particles. And then, of course, gravity is going to pull them down. In this container, he's got a positively charged plate, and down here, a negatively charged plate. And there's a little hole here so that the particles of oil, if they're falling just right, a few particles can fall through. Most of them are just going to make an oily mess on the plate up there. But a few of them are just going to fall through. As they fall through, they're going to get hit with some ionizing radiation, which is going to cause them to have a charge. Hit them with ionizing radiation. We've got a light source and a microscope so that we can look at these little particles. And with this positive charge and negative charge, you can control the charge on those plates, And these are getting a negative charge through this ionizing radiation. So a negatively charged particle is going to be attracted to the positively charged plate. Of course, gravity is pulling it down, and your electrical field is pulling it up. And so if you balance those two perfectly, you can get that oil drop to just hang in midair. So let's see how this video explains it. Come on. There we go.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhere to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
So that's a more typical science video, right? It's kind of dry and factual. Thank you. Okay, so any questions?
I just have one
Mhm.
about applying the charge to the electron.
Well, the electron has its own charge. So what he's doing here with the ionizing radiation is he's shooting electrons at the oil droplets, and some of them are sticking, and so the oil droplet gets a charge.
I see.
Yeah. Some oil droplets might have gotten 1 electron, 2, 3, 4 electrons, different charges, and so he could measure the charge on the oil droplets, and he found these different numbers. But if he found that if he took them all, they were all a factor of, or a multiple of this smallest number, and so that has to be the charge on the electron. And then using the mass to charge ratio, he was able to figure out the mass. So this is all of that in words. This is my there's this mysterious white square that shows up sometimes as some glitch in the computer. Loss of trained electrons or something. So this is all just stating all of that. I'm not going to make you do this on an exam or anything.